Computers are powerful machines. You might think that with current advances in computing, any problem can be solved by computers. But are there any problems that can never be solved by them? Take the example of software verification. Let's say you have written a Python program that sorts a list. You did a remarkable job with exception handling and want to verify if your program works as expected on all possible inputs. Turns out the general problem of software verification is unsolvable, meaning there is no generic software verification program out there that takes your program as input and says if you have written a program that works as expected for all possible inputs. Next time you see a blue screen, you can blame it on this undecidable problem. Alright, here is an intuitive explanation about why some languages are not Turing recognizable, or in other words, fully undecidable. From Church Turing's thesis, any computer program out there is equivalent to a Turing machine. All the programs you are capable of writing are finite in length, but there are infinite ways of writing a program that prints hello world. Okay? The set of Turing machines is countably infinite. For each Turing machine M, which can be defined using a 7-tuple, an encoded string of M exists which is finite in length. Just the way every program can be encoded into a finite length binary string in machine language. If you order these strings in terms of length and lexicographic order, you would see that they have one-on-one correspondence with natural numbers. Hence, the set of Turing machines is countably infinite. But what about the set of decision problems? I mentioned earlier that a decision problem is a yes or no question on an infinite set of inputs. If I were to write out sigma star as the set of possible inputs, every decision problem has a unique characteristic sequence that is an infinite length binary string of zeros and ones. With the help of diagonalization technique, we already saw that the set of infinite length binary strings is uncountably infinite. So we have countably infinite Turing machines to solve uncountably infinite decision problems. N number of Turing machines to solve R number of decision problems. Hence, computers cannot solve all decision problems. Moral of the story, instead of focusing on what we cannot solve, let us focus on what we can solve and solve it efficiently. That will be the focus of the chapter on computational complexity. Nevertheless, it is important to understand the class of decision problems that are unsolvable and to learn techniques for proving unsolvability. To start the discussion about undecidable languages, I will begin it with the ATM language. The problem of determining whether a Turing machine accepts a given input string, W. A more formal way of writing this is ATM equals to M, W, such that M is a Turing machine and M accepts the string W. Turns out ATM is undecidable. In the earlier lecture, I showed that some of the Turing recognizable problems are undecidable. Let's see if ATM is one of them. We can use a universal Turing machine that simulates the Turing machine M on input string W. If W is in the language of Turing machine M would end up in accept state and halt. That is when we can program the universal Turing machine U to end up in accept state and halt as well. But what happens when W is not in the language of Turing machine M. The Turing machine M can end up in reject state or end up in an infinite loop. This would push the universal Turing machine that is simulating M on W to end up in infinite loop as well. A simple analogy of this situation can be a Python program written by you can be thought of as M. The operating system with Python interpreter can be thought of as universal Turing machine U. If your program ends up in infinite loop, so does your operating system process that runs the Python program. Alright, now that you have some intuition of what ATM language is all about, let me prove that ATM is undecidable more formally. I will go with the technique of proof by contradiction. I will assume that there exists a Turing machine decider H that can solve ATM problem, meaning H takes the machine and word string and ends up in accept state if M accepts W, and ends up in the reject state if M does not accept W. Turns out, the machine description M is a valid string that can also be fed to the machine M. You may ask, why would anyone do that? Why feed a program with itself as an input? Here is a scenario. You are capable of writing a full-scale Python compiler program in Python language. Your Python compiler program reads input Python code and compiles it to machine language. As the Python compiler program you have written is also in Python, you can feed it as a string to itself. I'll give you some time to wrap your head around this statement. You can let the Python compiler you wrote to compile the Python compiler code you have written. With that, you can easily see that the Turing machine H ends up in accept state if M accepts its own machine encoding. H ends up in reject state if M does not accept its machine encoding. I should be able to fill in this table by running these sample Turing machines M1, M2, M3 and so on their respective machine encodings of M1, M2, M3 and so on. Now I'm going to design a Turing machine D which takes machine descriptions M as input and runs H which simulates M on itself. The Turing machine D can be hardwired to enter accept state if H rejects M on itself. D enters reject state if H accepts M on itself. Here is a formal description of the machine D. As D is also a Turing machine, you can feed D with its own description. Here is where we end up in contradiction. D enters accept state on D if D does not accept D. D enters reject state on D if D accepts D. Thus, neither D nor H can exist because it is the assumption that the decider H exists for ATM that got us till here. By proof of contradiction, we can confidently say that ATM problem is undecidable. I want you to rewatch this video and review the textbook proof multiple times to internalize this mind-blowing concept in theoretical computer science.